Hello everyone. In this lesson, we're going to learn about the basics of logistic regression and how to carry out logistic regressions using Python. Now, logistic regression is a classification model that's built on the same basic concept as linear regression. With linear regression, we took a linear combination of explanatory variables plus an intercept term to arrive at a prediction. So what linear regression was doing is it determined which constants, coefficients, or weights minimize the amount of error when making predictions on the input data itself. Now, in a classification problem, the response variable is categorical. We can't really use a linear regression to make a prediction for a category because categories don't have real numbered values associated with them. Now, the simplest case of classification is where the response variable is binary, meaning it can only take on two values, such as true or false. A logistic regression takes a linear combination of explanatory variables plus an intercept term, just like linear regression, but then it takes the result and passes it through a so-called logistic function or sigmoid function that basically squashes the output result into the range between 0 and 1. So the output of the logistic regression function then can be interpreted as a probability. Now, the logistic function itself looks something like this: 1 over 1 plus e to the minus t, where t is the linear combination or signal used in linear regression that we showed up here. Now, to get a better idea of what the logistic function is doing, I'm just going to create a plot of the sigmoid so that we can look at it a little bit. So you can see here that the sigmoid is an S-shaped curve where the values on the y-axis range from 0 to 1. So if you get too far down on the x-axis, you're basically going to be getting values of y that are around 0. So that's essentially equivalent to a 0% probability. And as the x values get higher, up to 6 and more, you're basically ending up with values after you map it with the sigmoid function that are very close to 1. Now, since we're using this sigmoid function to do binary classification, so basically deciding whether something is true or false, when we get a result that's very close to 0, that's telling us that the probability that there's a positive case or a true case is very close to 0. So in that case, if we were assigning a label to something and it had a result very close to 0, we'd assign it the label false because it's very unlikely that it is going to be true. And on the other hand, if we get a result close to 1, that's telling us the probability of a true or positive case there is very close to 100%. So in that case, if we were trying to assign a label to something and it had a result that was pretty close to 1, we'd probably assign it a prediction of true. Now, if we end up with a case where after passing it through this logistic function, the value is fairly close to 0, we're going to end up with something where we're not very confident whether it's in one bucket or the other. If it's actually at 0, well, 0 maps to 0.5, so that's 50%. So basically, if we get a result that says it's 0, that means as far as the logistic regression model is concerned, there's a 50-50 chance that it's a true or positive case or a negative case. Now, we're not going to go deeper into all the math of how logistic regression works in this video, or how you actually go about optimizing and fitting the function itself, because Python's packages to do logistic regression will do that for you. Really, the most important thing to know is that logistic regression is used for binary classification, and it outputs numbers between 0 and 1 that can be interpreted as the probability that a certain case is negative or positive. Now, to give a concrete example of logistic regression, for the rest of this video, we're going to revisit the Titanic disaster dataset and then apply logistic regression to the task for that dataset, which is to predict whether passengers survived or died in the Titanic disaster based on various features like, say, their gender, the fare that they paid, and things like that. So we're just going to start by loading in that data set. You don't have to concern yourself too much with all this code. It's simply loading in the data and doing some transformations so that the data is easier to work with. And now we're ready to use logistic regression to predict survival on this Titanic disaster data. So the scikit-learn library has a logistic regression model built into it. Now, before creating our model with the sex variable, we actually need to convert that categorical variable into a number using sklearn's preprocessing function called label encoder. So I'll show how to do that and then run the logistic regression below. So we're going to start by importing the necessary packages. So from sklearn, we're going to import the linear model. That will let us create the model itself. And also, we're going to import preprocessing because that contains that label encoder function that we'll use to preprocess the variables. So the first thing we're going to do is encode that sex variable as numeric so that the logistic regression function can use it. So to do that, you instantiate a label encoder by calling preprocessing.labelEncoder. We will then use labelEncoder.fitTransform on the column that we're using. So that is Titanic train, the sex variable. And now we can go about making our logistic regression model. To do that, we're going to start by initializing the model just like we did with linear regression. So we're going to say linear model.logistic regression. The solver argument here just specifies which method to use to solve the logistic regression problem. This shouldn't make a huge difference in terms of your model output. And then we can train the model just like we did with linear regression. So we'll take our log model.fit, and then we just want to pass it the relevant data. And then for our model output here, we get an intercept term and the coefficient or weight term for the one explanatory variable. Now, to make some predictions using the model we just created, we can do that using the predict or predict proba functions. So I'll show how to do that here. In this case, we're going to use predict proba, which means the predictions are going to output the predicted probabilities instead of the labels. So we're going to say log model.predictProba. For the argument, we pass in the data that we use to train the model. And then I'm just going to make a data frame out of those predictions and print a crosstab, which is basically going to be a table that shows us the output here. So the simple model came up with predictions that basically separated the data based on the gender of the passenger. Now, if we wanted to make a more complicated model that included some more variables, we can do that too, just like we did with linear regression. We just have to pass in a data set that has some additional columns. So we'll show how we could have done that. So we're going to take two of the other categorical variables here, the class and the cabin. We're going to encode those as variables that we're going to use. We're also going to pass in the age variable. Maybe a person's age had some impact on whether they survived or not. And with those extra variables now saved as trained features, we're just going to rerun them all the other model steps. The only thing that's changed now is that our data, trained features, has more features in it. So when we run the model this time, we get a different intercept, and notably the coefficients here, there are 4 of them because now there's 1 for each of the explanatory variables that we passed in. Now let's make some more predictions again using this model. And this time we're going to create a table of our predictions versus the actual outcome of whether people survived or not. So to do that, we're going to use predict this time instead of predict proba because we want the actual prediction, not the probability. So we're going to say log model.predict. We will pass in our trained features to make the predictions. And then to make our table, again, we'll say pd.crosstab, and we'll cross-tabulate the predictions versus the actual data as to whether people survived or not. This table here shows us what our model predicted on this axis, 0 meaning a negative case, and 1 meaning a positive case. In this case, negative means the person did not survive, and positive means they did survive. And on this axis is the true labels of survival, with the same 0 for not surviving and 1 for surviving. So this matrix tells us where the model got predictions right and where it went wrong. So in this first cell here, where the model predicted that the person did not survive, so a negative case, 0, and the actual label was also 0, that is called a true negative. True because the model got it right, and negative because the prediction was for a negative case. Now in the opposite corner here, we have a predicted value of 1, so that means survival, and an actual value of 1 as well, so that means the person did actually survive. This cell is known as a true positive. true because the model got it right, and positive because in this case it was predicting a positive case. So these two cells tell us where we went right, where the model prediction was actually the same as reality. The other two cells tell us where we went wrong. So in some cases, the model predicted 0, so that means it predicted the person did not survive, but the actual value was 1, so it means they did survive. We had 89 of those. That is what's known as a false negative. False because the model got the prediction wrong, and negative because the model predicted a negative case. But in reality, it was a positive case, that's why it went wrong. And we can also make errors the other way. In this cell here, the model predicted 1, so the model predicted that the person survived, but in reality, the person had a label of 0, which means they didn't survive. That is what's known as a false positive. False because the model got the prediction wrong, and positive because the model predicted the positive case, even though in reality, the negative case was true, so that's why it was false. Now this table here of predictions versus actual values is what's known as a confusion matrix. So we basically just went through and described all the different possible outcomes in the confusion matrix, but there are a lot of different metrics you can calculate based on those different cells that we talked about, the true positives, false positives, true negatives, and false negatives. There are many different metrics you can calculate using those values that can give you some insight into how well your model is actually doing prediction. Now, the most basic metric that you can pull out of that confusion matrix is the overall model accuracy. The accuracy of a model is just all of the true cases, so everything the model predicted right, which means both the true positives and true negatives, divided by the total number of cases. Since that's such a common metric to want to calculate, you can do that very easily using scikit-learn, just running .score on your logistic regression model. So we'll show how to do that with the model we made. All we have to do is take our log model, run .score on it, and then we just pass in our features that we used and the target. So when we run that, we see that our model has an accuracy of almost 80%. Now, overall prediction accuracy like this is just one of many quantities you can use to assess a classification model. Sometimes accuracy isn't the best metric to be using to assess a model. For instance, consider a model made to predict the occurrence of a disease that only occurs in 0.1% of people. A model that never predicts anyone has the disease would then be 99.99% accurate. But it wouldn't really help save lives at all because all you're doing is saying, hey, you don't have the disease because it's pretty rare. In this case, we might be interested in a different metric, such as the model's sensitivity, also known as recall, which is the proportion of positive cases that the model actually correctly predicts as being positive. Now, instead of generating a confusion matrix using a crosstab like we did above, since this is a very common thing to want to do, you can use it using sklearn metrics. So we'll show how to do that here. All you have to do is say from sklearn import metrics, and then metrics has a confusion matrix function. So you can run metrics.confusionMatrix. You pass in the true labels as the first argument, and then your predictions as the second argument, and it will generate the same confusion matrix table as a 2x2 array that we had above. And since there are many metrics that fall out of the confusion matrix aside from just raw accuracy, there is a function to pull out some of those metrics in sklearn called the classification report. So we'll show how to pull that up. We're going to call metrics.classificationReport. Again, we just pass in the true labels, the survived column, as well as our predictions. And when we run this, we see a little report with some different metrics in here. We have the precision, the recall. We discussed recall. Precision is a different metric that shows how many of the cases that were predicted as being positive are actually positive. And we also have this F1 score here. The F1 score is a bit more complicated of a metric that pulls in various different aspects of the confusion matrix that can kind of be seen as trying to have an overall summary of the strength of the prediction. So these are potentially good metrics to check in addition to raw accuracy when you're doing classification. And the metrics you may want to use could vary depending on the task that you're doing. In this case, for this Titanic disaster prediction competition, the metric used for the competition itself that's used to score the leaderboard is actually just raw accuracy. So for our purposes, for this specific case, accuracy is actually probably what we want to be using because the competition itself tells us what we should be shooting for. But when you're having to create a metric to optimize for yourself, you'll have to think harder about what makes sense for your application. Now, as a final exercise for this lesson, we're going to use the logistic regression model we made to actually make a submission for this Titanic disaster competition. So to do that, we're going to load in the test data. So this is data for this competition that has all the same columns as the train data, except for it doesn't have the actual label. It doesn't have the survive column, but it has everything else. So we can use our model to make predictions for this. So all we're doing here is we're loading in that data set and then using all the same pre-processing steps that we ran on the first part. And then in this next section, we're going to just convert the variables of interest to the encoded versions, and we're just going to pass that in to the predict function for the model we've already trained. That will allow us to make predictions on the test set that we can then use to submit to the competition. So in this last code cell here, all we're doing is we're taking the model we already trained, we're using it to .predict on our new test data. So now we have our test predictions. Then we just have to format a submission in the way Kaggle wants for this competition. All you need to do for this particular competition is submit a comma-separated values file that has a passenger ID column and a survived column with your predictions. So that's all we're doing. We're taking the test data passenger IDs. We're going to take our predictions, save it as a data frame called submission, and then all we have to do is say submission.toCSV. That will save this as a CSV file. And if we run this, this notebook will now generate a CSV file that can be used to submit to the competition. Now, I did go ahead and actually submit this file before I made the video, and it got a submission accuracy score of about 74%, which seems pretty good, which seems okay, except if you go and make a submission based purely on the gender variable, the very simple first model we made where we predicted all the males didn't survive and all the females did survive, that model actually has a slightly better accuracy than this one. So this goes to show you that adding new variables, like the age variable and class variables that we added to this final model, don't necessarily yield an improvement when you're applying the model to new unseen data. So in conclusion, logistic regression is a common tool for generating class probabilities and predictions based on those probabilities. And although logistic regression models are pretty simple and may not fully capture relationships between variables for many tasks, they're a good starting point because simple models tend not to overfit the data. So anytime you're dealing with a binary classification task, it's not a bad idea to start off with a logistic regression model as a baseline, and then you could compare other more complicated models you might make after that to your baseline. And if you can't come up with something that performs significantly better than the logistic regression model, well, you might be better off just using logistic regression because it's relatively simple. And simple models tend to be less likely to overfit on the training data. Next time, we're going to learn about another foundational classification technique called decision trees. So thanks for watching, and I'll see you again next time.